This research paper introduces the concept of tensorized block rational Krylov subspaces, which is an extension of the tensorized Krylov subspaces proposed by Kressner and Tobler in 2010. The main focus of this work is on solving tensor Sylvester equations, a type of multilinear matrix equation that arises in various applications such as control theory and the numerical solution of partial differential equations, PDEs. The paper begins by providing preliminary definitions and results about matrix polynomials, block rational Krylov subspaces, and tensors. It then proceeds to introduce tensorized block rational Krylov subspaces and their application for solving tensor Sylvester equations with right-hand sides that have low multilinear or tensor train rank. The authors also discuss pole selection strategies and present an efficient way to compute the residual. Finally, they test the developed methods on the numerical solution of discretized PDEs, such as the Poisson equation on a d-dimensional hypercube. The paper uses a highly technical and professional tone, employing domain-specific terminology and mathematical concepts throughout. It is written for expert researchers and stakeholders in the field of machine learning, artificial intelligence, and computer science. In the context of matrix polynomials and rational functions, a block characteristic polynomial of a matrix A with respect to a vector V is a matrix polynomial P, Z, such that P, A, hollow bullet V equals 0. Given a matrix A, a block vector V, and a sequence of poles xi k, the kth block rational Krylov space Qk, A, V, xi k, is defined as the set of all vectors R, A, hollow bullet V, where R, Z, equals P, Z, Qk, Z, and P, Z, is a matrix polynomial of degree less than or equal to K1. The block rational Krylov spaces are strictly nested, meaning Qk, A, V, xi k, is a subset of Qk plus 1, A, V, xi k plus 1, and the dimension of Qk, A, V, is equal to Kb. An orthonormal block basis of Qk, A, V, can be computed using the block rational Arnoldi algorithm, which iteratively computes the block columns of a matrix Vk plus 1 and two matrices Kk and Hk in block upper Hessenberg form, satisfying the relation AVK plus 1 Kk equals Vk plus 1 Hk. The symbols Kk and Hk denote the Bk times Bk head principal submatrices of Kk and Hk, respectively. In the realm of low-rank tensors, the representation of tensors in Tucker and Tensor Trains formats is crucial. A broader treatment of this topic can be found in 11 and 15. The block rational Arnoldi algorithm is essential for computing an orthonormal block basis of Qk, A, V, which is a fundamental step in various applications involving matrix polynomials and rational functions. The algorithm iteratively updates the matrices Vk plus 1, Kk, and Hk, allowing for the computation of these matrices in a structured and efficient manner. In the realm of tensor decomposition, the canonical polyadic, CP, decomposition is a fundamental concept, where a tensor is represented as a sum of rank 1 tensors. However, determining the CP rank of a tensor is n-fard. To overcome this issue, alternative definitions of rank have been introduced, including multilinear and tensor train ranks. The multilinear rank of a tensor X is defined as the vector k equals k1, kd, where k is the rank of the ith unfolding X, I. This can be associated with the Tucker decomposition, which decomposes a tensor into a chord tensor multiplied by matrices along each mode. The generators of a Tucker decomposition are denoted by G, B1, BD. The ith mode unfolding of the tensor can be written as X, I, equals big I. BD circled times by plus 1 circled times by 1 circled times B1, and the multilinear rank of X is component-wise smaller than K1, KD. The Tucker decomposition allows for data compression when k much less than ni for each I. The memory needed to store a tensor in Tucker format is O, K1, KD plus K1N1 plus KDND, which is beneficial compared to storing the full tensor. However, this representation becomes unfeasible for large dimensions. To overcome this, low-rank representations such as tensor trains have been introduced. A tensor train decomposition consists of a sequence of tensors, called carriages, such that x, I1, id, equals n array summation S1, SD1 G1, I1, S1, G2, S1, I2, S2, GD1, SD2, id1, SD1, GD, SD1, id. The numbers R1, Rod 1 are called the ranks of the decomposition. The tensor train rank of a tensor is defined as the vector R1, Rod 1, where re is the rank of x, I, obtained by grouping the first I indices of a tensor x as row indices and the remaining ones as column indices. For any epsilon greater than 0, every tensor y can be approximated by a tensor x in TT format with relative accuracy epsilon. Finally, a low-rank representation for x, I, can be derived, where x is a tensor in TT format with carriages, G1, GD. Any entry of x can be written as x, I1, id, equals a, I1, ij1, gj, ij, b, ij plus 1, id, or equivalently, x, I1, id, equals, bt, ij plus 1, id, circled times a, I1, ij1, vec, gj, ij. The paper discusses the solution of tensor-Sylvester equations using tensorized Krylov methods and introduces a novel approach by employing block rational Krylov subspaces. The authors generalize the procedure to solve the tensor-Sylvester equation x times 1a1 plus x times 2a2 plus x times dat equals c, where c has low multilinear or TT rank. They define tensorized block rational Krylov subspaces and establish a relationship between these spaces and rational functions. The main contribution is the introduction of block rational Krylov subspaces in tensorized Krylov methods, allowing for the treatment of C with more than one column and providing flexibility in the choice of projection subspace through pole selection. The paper begins by defining the tensorized Krylov subspaces, which can be described using multivariate polynomials. The authors then introduce the tensorized block rational Krylov subspaces, which are defined as a sum of terms involving the block rational Krylov subspaces QKI, I, C, for each I equals 1, D. This definition allows for the inclusion of block vectors C with more than one column, making the method more versatile. A key aspect of the paper is the relationship between tensorized block rational Krylov subspaces and rational functions. The authors define an extension of the operator hollow bullet to multivariate polynomials and show that the tensorized block rational Krylov subspaces can be represented as the image of a specific rational function applied to matrices A1, AD and vectors C1, CD. This representation is crucial for understanding the properties of the solution X and its approximation using low-rank tensors. The authors also analyze the effects of using extended Krylov subspaces in the construction of tensorized Krylov subspaces, providing insights into how different choices of poles can influence the approximation of the solution. Furthermore, they provide a detailed explanation of the algorithm for solving the tensor-Sylvester equation, which involves solving the projection of the equation into the tensorized block rational Krylov subspace. The paper concludes with a discussion on the limitations and assumptions of the proposed method, as well as potential avenues for future work. The use of tensorized block rational Krylov subspaces offers a promising approach to solving tensor-Sylvester equations, particularly when dealing with low-rank tensors. The paper's findings contribute to the development of efficient algorithms for solving large-scale linear systems and eigenvalue problems in computational science and engineering. The paper discusses the development of a novel method for solving tensor-Sylvester equations, utilizing tensorized block rational Krylov subspaces. These equations are essential in various fields such as computational physics, signal processing, and data analysis. The proposed approach leverages the block rational Krylov subspace method to approximate the solution of a tensor-Sylvester equation, which can be expressed as x times 1a1 plus x times 2a2 plus x times d at equals c, where c is a tensor with low multilinear or tensor train rank. The key idea behind this method is to construct an orthonormal block basis for the tensorized block rational Krylov subspace, denoted as V equals Vd circled times Vd1 circled times V1. This basis is computed using the block rational Arnoldi algorithm, which involves choosing suitable block vectors C for each dimension I. The solution X is then approximated by the tensor xk equals yk times 1 v1 times 2 times dvd, where yk solves the projected tensor Sylvester equation yk times 1a, k1, 1 plus yk times dA, kd, d equals ck, with a, key, I equals vhiai for each I. To analyze the convergence of the tensorized block rational Krylov method, the authors consider the vectorized form of the tensor Sylvester equation, X equals C, where A is a matrix defined in terms of the matrices I, and X and C are vectorizations of X and C, respectively. The residual of the solution is given by R, V, A1, add, C, equals CAVY, where Vy is the vectorization of the tensor Yk that solves the projected equation. A representation of the residual that depends on the poles of the rational Krylov subspaces is also provided, utilizing proposition 2.2 from 2. This representation is crucial for understanding the convergence properties of the proposed method. The paper also highlights the importance of adaptively determining the poles for the method and computing the residual, which are discussed in detail in sections 4 and 5. Furthermore, the authors emphasize that the solvability of the original tensor Sylvester equation does not guarantee the solvability of the projected equations, and a sufficient condition to avoid this issue is to require that 0 not an element W, A1, plus W, A2, plus W, add, where W, A, denotes the numerical range of a matrix A. However, verifying this condition can be challenging in practice, and the authors suggest changing the projection space as a possible remedy if the projected equation is not solvable. The residual R can be represented as the sum of the vectorial products of the vectors V and VH, where VH is the vectorization of the tensor Re. The Euclidean norm of VH is equivalent to the Frobenius norm of the ITH mode unfolding of Re. This is a corollary of proposition 3.6, which states that the squared Euclidean norm of the residual can be written as the sum of the norms of the matrices Re, with the remainder term vanishing for C in the span of V. The convergence of the method is related to the norms of these matrices, which are solved by projecting I into the block rational Krylov subspace QKI, A, C. This process is further detailed in the context of Tucker and Tensor Train formats for the right-hand side C. The main advantage of Tensor Train format is the ability to handle more summands in the tensor Sylvester equation, with the need for an approximate solution in TT format as well. The solution involves solving the projected tensor Sylvester equation, which can be done using algorithms like AMEN to keep the solution in TT format. The research focuses on techniques for pole selection in block rational Krylov subspaces, particularly for matrices in Tucker or TT format. It builds upon corollary 3.8 in remark 13, minimizing the norms of residuals from Sylvester equations. The approach involves simplifying theorem 6.1 from 5 to represent the norm of the matrices with a formulation involving chosen poles. The authors assume the first pole in each block column equals infinity, allowing for monitoring convergence via Frobenius norms. Two methods are proposed for pole selection, det and det2. The latter, which involves minimizing a rational function with a smaller degree, shows comparable or better performances in numerical experiments. The field of values of the matrix BI is discussed, and its determination is simplified by substituting it with the convex hull of the union of eigenvalues of A, Kj, for J, lec I. The computation of the residual is addressed, and a lemma is provided for cheaply computing partial residuals when the last pole is infinity. This work contributes to the development of efficient algorithms for solving Sylvester equations in Tucker or TT format. Here is a combined summary of pages 15 and 16 of the research paper. The authors present a tensorized block rational Krylov method for solving tensor Sylvester equations. They derive an expression for the norm of the residual, which involves the solution of a projected equation and the computation of certain matrices and tensors. The authors then provide numerical results for the convergence of the presented algorithms, using the MATLAB code made available at https://github.com/numpy/tbrksylvester. The first test problem involves computing the approximate solution of the Poisson equation on a d-dimensional hypercube, discretized with a uniformly spaced grid. The resulting Tensor-Sylvester equation is solved using the tensorized block rational Krylov method. The authors also consider a second test problem, the convection diffusion partial differential equation, which leads to a non-symmetric Tensor-Sylvester equation. The numerical simulations are run on a server with Intel Xeon CPUs and 256 GB of RAM, using MATLAB Art 2021 with the Intel Math kernel library. The experiments employ different choices of poles, including det, det2, poly, and ext. The computation of rational Krylov subspaces uses the arcade toolbox, and the maximization problems are solved by maximizing the functions on a sampling of the boundary of the set described in Remark 4.2. The numerical results show the behavior of the relative norm of the residual by varying the number of Arnoldi iterations, for different choices of poles and sizes of the discretization grid. The results are presented in figures 1 and 2 for the Poisson equation and convection diffusion equation, respectively. The authors note that complex poles can appear in the case of non-symmetric matrices, and they refer the reader to 17 for a more complete discussion. Here is a combined summary of pages 17 and 18 of the research paper. The authors present numerical results for solving discretized Poisson and convection diffusion equations using TUC-TBRK and TT-TBRK methods. Figure 1 demonstrates the behavior of the relative norm of the residual produced by solving a discretized Poisson equation of dimension d equals 4 with f equals 1, 1 plus x1 plus x2, 1 plus x3 plus x4, employing TUC-TBRK methods with different choices of poles. Table 1 shows the iterations and time needed to reach a relative norm of the residual less than 10(4) and 10(6) for the solution of a discretized convection diffusion equation of dimension d equals 3 with f equals 1, 1 plus x1 plus x2 plus x3, employing TUC-TBRK methods with different choices of poles. The complex poles are employed coupled with their conjugates to guarantee real arithmetic, which may result in different numbers of Arnoldi iterations. Figure 3 illustrates the behavior of the relative norm of the residual by varying the mean number of Arnoldi iterations for the solution of a three-dimensional discretized convection diffusion equation using different choices of poles. The TT-TBRK methods are implemented in MATLAB using the TT toolbox to manage tensors in TT format. Figures 4, 5, and 6 show the behavior of the relative norm of the residual for different scenarios, including varying the number of Arnoldi iterations, the size of the discretization grid, and the mean number of Arnoldi iterations. Figures 2 and 3 on page 18 demonstrate the behavior of the relative norm of the residual produced by solving a discretized Poisson equation of dimension d equals 3 with f equals 1, 1 plus x1 plus x2 plus x3, employing TUC-TBRK methods with poles chosen accordingly to det for different sizes of the discretization grid and by varying the mean number of Arnoldi iterations for a discretized convection diffusion equation of dimension d equals 3, respectively. These results highlight the effectiveness of the proposed methods in solving high-dimensional problems. The research paper discusses the characterization of tensorized block Krylov subspaces using multivariate rational functions and develops a method for solving Tensor-Sylvester equations. It presents the behavior of the relative norm of the residual produced by solving the discretized Poisson equation with different choices of poles. The TT-TBRK method is employed, showcasing its potential for solving high-dimensional PDEs. The paper also compares the execution time and accuracy between TT-TBRK and AMEN for solving the Poisson equation. The results indicate that TT-TBRK is more efficient and accurate for higher dimensions. The study further reports on the time and number of Arnoldi iterations required for solving high-dimensional Poisson equations using TT-TBRK. The findings demonstrate that the number of iterations does not grow with the increase in space dimension, highlighting the efficiency of the algorithm. The paper presents a novel approach to solving Tensor-Sylvester equations using the block rational Krylov subspace method. This method is particularly suited for large-scale linear systems with tensor product structure, leveraging the low-rank approximations and Kronecker product structure inherent in these systems. The authors provide an in-depth analysis of the convergence properties of this approach, as well as strategies for pole selection and efficient computation of residuals. The block rational Krylov subspace method builds upon existing techniques such as the rational Krylov algorithm and alternating minimal energy methods. It utilizes Galerkin projection onto a tensorized block rational Krylov subspace, allowing for the solution of tensor Sylvester equations with reduced computational complexity. The authors also discuss the implementation of their algorithm, which has been made publicly available at https://github.com/numpy/tbrksylvester. This code integrates with the TT Toolbox software for Tensor Train decomposition, further expanding the capabilities of the proposed method. In addition to the theoretical development and implementation, the paper provides a comprehensive review of related literature, including works on matrix equations, Kronecker product structure, and tensor decompositions. This includes references to key papers on the multilinear singular value decomposition, the rational Krylov algorithm, and the alternating minimal energy method, among others. Overall, the paper contributes to the advancement of numerical methods for solving large-scale linear systems with tensor product structure, offering a powerful tool for researchers and practitioners working in this area. The proposed block rational Krylov subspace method demonstrates promising potential for solving high-dimensional tensor problems, including those involving multi-term Kronecker structures.